Hi friends, this is Venkatesh from site CC Institute of Technology and Engineering, 2nd BTech IT. In this video, I gave an idea about the solution for an Hamiltonian cycle using backtracking. Here is an example, we done it later. First of all, we discuss about what is Hamiltonian cycle and what is backtracking. Hamiltonian cycle. It is a path in a graph that visits each vertex exactly once and returns to the starting vertex, forming a closed loop. Here, the cycle tells that the first vertex of a graph should visit once and then the last vertex should be connected to the first vertex. A Hamiltonian cycle, also known as Hamiltonian circuit. Next, we discuss about the backtracking technique. The backtracking technique is a general algorithm technique used for finding the solutions to problems that involve exploring all the possible paths or the combinations. Here, the adjacent matrix for the given graph. For the above given example, we need to solve the graph with the help of backtracking. Let us get into the problem. Let us consider the source node A. A has two adjacent vertices, one is B and another one is D. First of all, the backtracking means we have to follow DFS, depth first search. We have to start at the particular node. We have to move to its deepest level as long as there is a node. If there is no node to explore, then we have to perform the backtracking. That means we have to backtracking its previous node and explore the nodes of the deepest node. Let us consider the B. For B, there is three adjacent vertices. One is A and another one is G and another one is C. A is already visited, so we didn't write. We write the G and C. For G, there are four adjacent vertices. One is B and then C and D and E. B is already visited, so we didn't write. We write D, C, and E. For C, there are three adjacent vertices. One is B and G and F. B is already visited and G is also already visited. So we didn't write both of them. We write F. For F, there is two adjacent vertices. One is C and another one is E. C is already visited, so we didn't write. For E, there is three adjacent vertices. One is G and F and D. G is also already visited and F is also already visited. D is not visited, so we write. For D, there is three adjacent vertices. One is A and G and E. G and E, both of them are visited, so we didn't write. We write A. For this path, the starting source node is A and the end of the node is also A. So it is Hamiltonian cycle. Let us consider the G of another vertex D. D having three adjacent nodes. One is A and G and E. The G is already visited and A is also already visited. So we write E. For E, there is three adjacent vertices. One is D and G and F. The G is already visited and D is also visited. We write F. For F, there is two adjacent vertices. One is E and another one is C. Okay. E is already visited, so we didn't write. For F, we write C. For C, there is three adjacent vertices. One is B and G and F. B is also B and G and F, both three are listed. So we didn't write any of them. So it not follows the cyclic form. Let's check for the another vertices of G is E. For E, there is three adjacent vertices. One is D, G, and F. G is already visited, and D is D and F. For D, A and G, E. Three are visited, so we didn't write any of them. For F, the C, for F, the C, and E are two adjacent vertices. The E is already visited, so we didn't write. For F, we write the C. For C, there is three adjacent vertices B, G, and F. B is already visited, and G is also already visited, and F is also visited. So we didn't write any of them. So it does not form the cyclic form. So it is not a Hamilton cycle. Mean cycle. Let us go to next step. For the step 2, we need to check the adjacent vertices for the vertices B of C. For C, we have three adjacent vertices B, G, and F. B is already visited, so we didn't write B. Then we write G and F. For F, there is two adjacent vertices. One is C and another one is E. C is already visited, so we didn't write, and we write E. For E, there are three adjacent vertices. One is G and F and D. F is already visited, so we didn't write. We write D and G. For G, there are four adjacent vertices. One is B and C and D and E. The B, C, E are three visited, so we didn't write any of them. We write D. For D, there are three adjacent vertices. One is A and another one is G and another one is E. For D, G and E are visited, so we didn't write. We write A. For this part, it performs the backtracking. A is performing the backtracking D, and D is performing the backtracking G, and D is performing the backtracking D, and E is performing the backtracking F. F is performing the backtracking C, and C is also performing the backtracking B, and B is performing the backtracking A. So this is an Hamiltonian cycle using backtracking. Let us check for the another vertices of E is D. For D, there are three adjacent vertices. One is A and G and E. For D, A and E are visited, so we didn't write. We write G. For G, there are four adjacent vertices B, C, D, and E. These four are visited, so we didn't write any of them. So it is not an Hamiltonian cycle because uh, it does not forms a closed loop. Let's come to up and let's check the adjacent vertices for the C of G vertices. The G having the four adjacent vertices, one is B, C, D, and E. The B and C are already visited, so we didn't write. We write D and E. For D, there are three adjacent vertices A and G and E. A and G are both are visited, so we didn't write. We write it as E. For E, there are three adjacent vertices. One is G and D and F. D and G are both are visited, so we didn't write. We write F. For F, C and E are the two adjacent vertices. Both vertices are visited, so we didn't write. It is also not a cyclic form. It is also not be in the cyclic. So then we check for the next G and E. For E, there are three adjacent vertices G, D, and F. For E, G is already listed, so we didn't write. And there are two D and F. For D, there are three adjacent vertices A, G, and E. Three are listed, so we didn't write any of them. For F also, there is two adjacent vertices C and E. C is also listed and E is also listed. We didn't write any of them, so it will also not form the cyclic form. So it is not an Hamiltonian cycle. Like that, for above steps, we need to done the same as for the step 3 also. In the step 3, the Hamiltonian cycle, the pathway is A performs the backtracking of B, and B is perform the backtracking of G, and G is performing the backtracking of C, and C is back performing the backtracking of F, and F is back performing the backtracking of E, and E is performing the backtracking of D, and D is performing the backtracking of A. So this is the Hamiltonian cycle for the step 3. As same as step 3 we did for step 4 also. In the step 4, the Hamiltonian cycle, the pathway is A is performing the backtracking of B, and B is performing the backtracking of C, and C is performing the backtracking of F, and F is performing the backtracking of E, and E is performing the backtracking of G, and G is performing the backtracking of D, and D is performing the backtracking of A. In this, it forms a closed loop, so it is a Hamiltonian cycle using backtracking. In this graph, we have four Hamiltonian cycles are given in below. When we observe the all four Hamiltonian cycles are start with A and end with A, it seems to be cyclic. These are the all possible Hamiltonian cycle for the given graph using backtracking. Thank you.